Hello, my name is Rapp. I'm a PhD student at Karlsruhe Institute of Technology in Germany. This is a presentation of our recent technique, SmartBoost. The voltage and frequency levels of the CPU cores have a large impact on the performance of the running applications, but also on the consumed power and on the temperature. Avoiding high temperature is the key limiting factor in modern processors. This makes boosting, which we target in this work, a crucial part of resource management. Boosting selects per core voltage and frequency levels through DVFS in order to optimize the performance under a temperature constraint. Existing boosting solutions are suboptimal, as we will see in a moment. For instance, the state of the practice, Intel Turbo Boost, simultaneously increases or decreases voltage and frequency levels of all cores without considering the characteristics of the applications running on these cores. As we will see, different application characteristics let some applications benefit more from boosting than others, which can be exploited by assigning different VF levels to different cores. While there are several state-of-the-art research techniques that consider application characteristics to select VF levels in a more targeted manner, they do this incompletely. The following motivational example visualizes this. Most state-of-the-art techniques perform boosting based on the retired instructions per second IPS of applications. The intuition is to boost applications with high IPS because they tend to be more compute-bound and benefit more from an increase in the frequency. This is not always optimal, as the following example shows. We execute two applications from Splash, LU-Cont and Radix, in parallel, both running at the same frequency of 2 GHz. Radix has a very low IPS and finishes in around 200 milliseconds, while LU-Cont has a very high IPS and finishes in around 400 milliseconds. Their power consumption follows a similar pattern. We show now that boosting the low IPS Radix is beneficial. Boosting Radix decreases its execution time by 33% to around 140 milliseconds. LU-Cont is throttled during the execution time of Radix in order to maintain the same peak temperature on the chip, which is 57 degrees in this example. Its execution time is increased slightly by only 2%. As a result, boosting the application with low IPS significantly increases the overall system performance, unlike what would be expected. Why is this the case? There are two reasons. First, Radix has a low power consumption and is not executing on the thermal hotspot of the chip. Increasing the VF level of its cores only has a small impact on the peak temperature. This small impact can already be countered by slightly throttling the high-power LU-Cont. In this example, an increase by 1 GHz in Radix is enabled by throttling LU-Cont by only 100 MHz to maintain the same peak temperature. The takeaway message from this is that the sensitivities of the power and peak temperature on the VF level change need to be considered. The second reason for this unintuitive boosting decision to be beneficial is that Radix is compute-bound despite having low IPS. It therefore benefits strongly from being boosted. The second takeaway is that not the absolute values of IPS, but the relative sensitivity on the VF levels have to be considered. The sensitivities of performance, power and temperature play an important role in our work. Let's look into these in more details. These graphs show how performance and power depend on the frequency for three applications, LU-Cont and Radix that we already saw earlier, and Henkel from Parsec. These applications have very different characteristics. The performance impact of changing the frequency, for example from 2 to 3.5 GHz, is very different. While Radix gets 71% faster, Henkel only gets 33% faster. Large differences can also be seen for the power. The power of LU-Cont increases by 4.4 watt, while the power of the other two increases by less than 1 watt. We observe a large variation between the applications. Also, these two metrics are not interchangeable. For example, Radix and Henkel have almost indistinguishable power, but the sensitivity of their performance differs a lot. Additionally, these metrics vary throughout time with the application execution phases. We tackle these non-trivial application properties with machine learning. More details on this follow later. Boosting optimization must consider three metrics: The first two are the sensitivities of power and performance on the frequency. These two depend on the application, but they cannot be measured directly during execution of an application. The third metric is the sensitivity of the peak temperature on the power. This depends on the application mapping and the position of the thermal hotspot. These metrics may be contradictory. For example, an application may have a high sensitivity of the performance, making it a good candidate to boost, but also a high sensitivity of the power, making it a bad candidate to boost. To solve this, all three metrics must be considered jointly. We are the first to jointly consider all these three metrics within the boosting optimization. Our contribution has two main parts. We introduce a novel metric that we call boostability that integrates the three metrics. And we design, train and use a multitask neural network to estimate the application-dependent sensitivities of performance and power. We then develop a boosting technique, SmartBoost, that is based on these two contributions. We start with the first contribution, the boostability metric. As a refresher, our objective is to maximize the performance under a temperature constraint using DVFS. We now introduce three mathematical symbols. The first one is the sensitivity of the performance as perf of a thread. It is measured in percent per gigahertz and indicates how its performance changes with the frequency. A frequency change affects also the hotspot temperature via the power consumption of the thread and the thermal properties of the chip. The second symbol, SPW, is the sensitivity of the power, which is measured in watt per gigahertz. The thermal properties of the chip are described by a thermal model. We use the well-established RC thermal model, which expresses the steady-state temperature T by a linear equation that essentially multiplies the power vector P, containing the power consumption of different parts of the processor, for example the cores, with the matrix B inverse. The sensitivity of the temperature of the hotspot H on the power is the derivative of this equation with respect to the power of the core I that the thread is running on. This is simply one entry of this B inverse matrix. Its unit is degrees Celsius per watt. We define now our novel boostability metric B. The thread that we want to calculate the boostability for is running on core I, the hotspot is currently on core H. The boostability is defined by the equation on the slide that combines all three sensitivity metrics. The resulting unit is percent per degree Celsius. Intuitively, this metric expresses how much the performance of a thread changes relative to how the hotspot temperature changes if we modify the frequency of the thread. As general rules, we should boost threads with a high boostability, which means high performance gains for small temperature increase, and we want to throttle threads with a low boostability, which means small performance losses for a high temperature decrease. Making boosting decisions based on this boostability metric is the first core contribution of our paper. Calculating this metric requires knowing the performance and power sensitivities of the applications. These two metrics vary between different applications, as we saw earlier. And they cannot be measured directly at runtime during the execution. The only way to measure them is to change the VF levels and observe how performance and power change, but such a sampling-based approach is not viable to do at runtime because application characteristics change over time with application execution phases, which would require periodically testing each VF level for every application. Because we target unknown applications, it is also not possible to do offline profiling for every application. To solve this problem, we design and train a neural network model that estimates the sensitivities of performance and power based on performance counter readings. The two metrics are not interchangeable, as we saw earlier, but they are still related. We exploit this by training not two independent models, but one joint model that estimates both. Besides improving the generalization, it also reduces the runtime overhead compared to two separate models. To create training data, we execute applications at different frequencies to obtain their traces. To consider that application characteristics, which includes the sensitivities of performance and power, may change over time, we divide these traces into slices and compare performance and power of the same slice at different frequencies. We now have all the ingredients to develop our runtime boosting technique with the name SmartBoost. It starts by reading performance counters of the running threads and invokes the sensitivity model. Using the estimates of the sensitivities of performance and power, and the sensitivity of the temperature that comes from the mapping in the thermal model, we calculate the boostability. This is done for every thread to get the boostabilities of all applications. Then our technique traverses 3 phases. First, we throttle applications if it is required to avoid thermal violations. Here we select applications with low boostability, as explained earlier. Next, we boost applications if thermal headroom exists that can be exploited. This step selects applications with high boostability. When there is no thermal violation, but also no exploitable thermal headroom, still the current VF levels may be suboptimal. We check in the third step whether it is beneficial to throttle an application with low boostability to be able to boost an application with high boostability to increase the overall system performance. This process is repeated periodically, in our case every millisecond. Importantly, this technique is designed to cope with unknown applications for which no offline traces are available. The key contribution to achieve this is to use the neural network-based sensitivity model. And the second point that I like to highlight again, because it is important, is that we jointly consider the sensitivities of performance, power and temperature to make the boosting decisions. The key contribution to achieve this is the boostability metric. We evaluate our technique in the hot sniper simulator, which extends sniper with periodic power and temperature estimation. We simulate a many-core processor with 64 cores that are operated at frequencies from 1 to 4 GHz in steps of 100 MHz. The critical temperature is set at 80 degrees Celsius. We compare our technique against the state-of-the-art technique DTPM and against the state-of-the-practice Intel Turbo Boost. First, we evaluate the performance of a mixed workload that consists of 20 randomly selected applications from Parsec and Splash. These applications arrive at random arrival times following a Poisson distribution. We vary the average arrival rate to study different system utilization values. We observe that for all arrival rates, SmartBoost achieves the lowest average response time, which means the highest performance. It improves the performance over DTPM by 21% on average and by 25% over Turbo Boost. Turbo Boost does not at all consider application characteristics, resulting in the lowest performance. DTPM differs from SmartBoost in not considering all 3 relevant metrics, performance, power, temperature, jointly for boosting or throttling. For instance, it only considers the sensitivity of the performance when selecting the application to throttle without taking into account power or temperature. Another advantage of SmartBoost over DTPM is its sensitivity model. Both DTPM and SmartBoost use performance and power models. We evaluate the error of these models to obtain even further insights. 4 applications from Parsec and Splash have not been used for training and are used now to test the models. DTPM uses a linear performance model, while SmartBoost uses a neural network model. This neural network model achieves a much lower prediction error, which is less than 1% per frequency step on average. DTPM has a very detailed leakage model, but uses simple V²F scaling for the dynamic power, not taking into account that the switching activity changes with the frequency. We observe that the model in SmartBoost also has a much lower prediction error for power, which is only 13 mW per frequency step on average. These experiments show the benefits of using a neural network model for estimating these metrics. This comes at the cost of a slightly higher runtime overhead. Nevertheless, the runtime overhead of SmartBoost is less than 1% and therefore negligible. In conclusion, we study boosting of a many-core processor, which uses DVFS to maximize the performance under a temperature constraint. We found that the boosting optimization must jointly involve performance, power and temperature, and our technique SmartBoost is the first to do so. Our 2 main contributions are a novel boosting metric, the boostability, to jointly consider performance, power and temperature in a single metric, and a neural network model to estimate the application-dependent sensitivities of performance and power. Please check our paper for more details, or directly approach us if you are interested in our work.